Well, what we want to do today is basically continue to build on what we understand about this thing called the fundamental theorem. Remember in our last lesson we figured out that basically the highest exponent, that's called the degree, the highest exponent is going to tell us exactly how many roots we have for our equation. And of course we also tied that into the graph, and ultimately we have what's known as the connection between roots and zeros and the graphs of polynomials, again, all tied together with the fundamental theorem. But there's a little bit more, actually maybe more than a little bit more, but there's more. And so what I want you to do is take your note paper from yesterday and flip it over. We're also going to change the color here. It doesn't matter what color you have, just flip it over. And at the top half of the paper, let's have a discussion about what's called division and depression. Now, I'm talking about mathematical division and also mathematical depression. So how can division, and you'll see this concept of depression, help us to be able to solve a polynomial and tie it all together into the fundamental theorem? Well, I'm glad that you asked. The first thing is that you're going to find out that we start a little differently. We start with a root. You actually be given a root. You know, I'm talking about like you're going to be given one of the answers that we're trying to find in the problem. So suppose we have a polynomial, perhaps something like x cubed minus 19x minus 30. And you're given, this is really nice now, you're given that x equals x equals negative 3 is a root. How can I use that? I forgot the word is. How can I use that to help me solve for the rest of the roots and really understand the whole graph and the fundamental theorem? Well, I'm glad you asked. The answer is we're going to use division, and we're going to end up with a polynomial that is depressed. It's actually quite neat. We're simply going to divide this negative 3 into our polynomial. Now you can see that what I'm getting set up for here is known as synthetic division. And these green numbers that I'm helping you to locate are the coefficients. Remember, when you use synthetic division, you just need the coefficients of your polynomial. Now, I did skip, there was a missing coefficient, so I had to use a placeholder. That's that 0 that was written down. But now I'm going to do this process of division where you bring down the first number, and after you bring it down, you multiply. And after you multiply, you add. Remember, you add these numbers, and then the process starts over. You're going to multiply here, and then add, and finally multiply and add. And you'll notice that we get a remainder of 0, which is good, because that means that these coefficients that I got created a depressed polynomial. You see, I started with a degree 3 polynomial. I started with a degree 3. That means that now I'm down to a degree 2. I'm down to 1x squared minus 3x minus 10. Again, this is my depressed polynomial. But it's not feeling bad. It's actually quite happy because it's able to be solved. That's right. I'm able to actually solve this equal to 0 using, as you can see, using a factoring technique. Yes, because I ended up with a smaller solvable polynomial. In fact, let's stop right here. I want you to realize that this division that we did gives us a depressed polynomial that is simpler and solvable. And that's exactly what we're going to do now. We're going to factor, and we're going to solve this polynomial. by thinking about numbers that multiply to be negative 10 and add to be negative 3, right? So we get negative 5 and plus 2. But now I can continue to solve for my remaining zeros. My remaining zeros, which come out to be 5 and negative 2. Now, do you remember that root that we were given? How we were given negative 3? Well, that also makes the list. And how many zeros are in my list? That's right. 1, 2, 3 zeros. Was I supposed to have 3 zeros? 100% 3 zeros, because that's my degree. And so I can actually use division to create a depressed polynomial, which ends up being able to be solved. In this case, we solved it using factoring and ended up with our list of zeros. And where should those zeros show up? That's right, they should show up on the graph as the x-intercepts. Isn't this kind of neat? Yes, we're going to have a graph that has these 3 x-intercepts. And all I got to do now is think about the fact that the graph's going to go up to the right. It's going to do the opposite thing to the left. And, well, when I snake my way through these points, I'm able to connect those end behaviors. And by the way, the number at the end is the y-intercept, and that even looks like it makes sense because my y-intercept needs to be negative, in this case negative 30. So if I'm given a root, I can divide by that root, and I can end up with a smaller solvable equation. Well, that's kind of neat. That's one way that I can add to this fundamental theorem. What about if I give you a polynomial, perhaps the polynomial x to the 4th? Let's make sure you can read this here. So start over. What if I give you p of x equals x to the 4th minus x cubed minus 28x squared plus 8x plus 160. Goodness, it's a gigantic polynomial. And what if I give that to you and just say, here, solve it, graph it, make all the connections with the fundamental theorem? What are you going to do? In the previous problem, I gave you a root. And you started with that root, but it looks like I'm not giving you anything. What am I going to do? What am I going to start with? How am I going to solve this? Well, the truth is, you do need something. You always need something. And if I don't give it to you, maybe you need to give yourself a graph. Maybe you need to make a graph. You see, we can actually use a graph sort of at the front end. In other words, we can start with a graph, and perhaps something on the graph will help us to be able to find all of these roots and understand how the fundamental theorem connects. So this is going to be a great time for us to go to Desmos. We're going to graph this polynomial and find out how we can use the graph to help us get started. So we're typing the polynomial into Desmos. Remember, when I do this on the iPad, I actually can't type these exponents in without cheating a little bit with the keyboard. So I'm typing in x to the 4th minus x cubed minus 28x squared. Keep going here, plus 8x. You can type this in also, and then eventually plus 160. So just double checking that I typed all that in right. Now, you may need to zoom out a little bit. You may need to adjust your window. And in that case, whether you're using your phone or maybe using your computer, you can manually make your x values go from about -10 to 10. Honestly, usually the numbers we're looking for are going to be between -10 and 10. But perhaps my y values need to stretch a little bit, and that's why you can see that my graph is actually going up as high as 150, and kind of down to negative 50. Now, this is the graph of the polynomial equation. How do I use this graph to be able to get myself started with all these roots and the fundamental theorem? Well, wouldn't it be slick if I maybe used one of the roots that was on my graph? Yeah, like 5. I notice one of the roots that's already on my graph. And then look over here. It looks like there's one at negative 4. See, what's happening is I'm using my graph to actually locate what we call like a starting root. And what I'm doing is I'm picking the ones that I'm pretty sure of. Again, it looks like 5. And it looks like over here, negative 4. Now, if you're saying, but there's some other roots, there are, but I don't really know what those are. So instead, I'm going to use the roots that I'm sure of, and we're going to call those starting roots. So when you're doing a problem like this, you're going to want to show some of your work and basically a little sketch of the graph and locating, or I should say labeling, these roots that we decided to start with. And then I can take those roots and I can use them to begin my division. So again, if you're given a graph, or better said, you need to give yourself a graph, you're going to pick some starting roots. And those starting roots are going to allow you, once again, to get started with division. What do I mean? Well, exactly what we just did in the last problem. You're going to divide by 5 using synthetic division, using the coefficients of your big old polynomial. And if you're saying, why are you starting with 5? Why didn't you start with negative 4? The answer is, it doesn't matter. You actually could have started with either one of the roots, but I'm choosing to start with 5. It's kind of the first one that I saw, and I'm going to begin this process of division. As I do this process of division, I'm hoping that I end up with a remainder of 0, because a remainder of 0 is going to tell me that it divided evenly. Now, 5 32s actually come out to be negative 160. That's perfect. A remainder of 0, I get a depressed polynomial. Now, instead of writing down the sort of the value of my depressed polynomial, that is writing down something to the effect of maybe 1x cubed and 4x squared, and instead of actually writing this down, what I'm going to do is I'm going to realize that I need to divide again. Yeah, I'm going to divide again. I'm going to divide by my next root. See how this works? You can continue your synthetic division. In other words, you can depress your polynomial one more level. And so I'm going to use negative 4 as my next root. That's because I saw that on the graph. And I'm going to do this process of polynomial division. It's actually synthetic division. And I'm hoping to get a remainder of 0. And once again, I do. Now, I get my final depressed polynomial. My final depressed polynomial that I can record now as 1x. 1x. Now think about it. I started with x to the 4th. I divided once, twice. That means that my equation has been depressed by 2 exponents. So if I started at 4 and I depressed it twice, I'm now down to a 1x squared. Now, this would be a 0x. I'm not going to write a 0x, but this would be minus 8. And I've got myself a polynomial that is simpler and solvable. What do we mean simpler and solvable? Well, I mean setting it equal to 0 and solving for the remaining roots. You know, like adding 8 to both sides and getting x squared equaling 8. And how about taking the square root of both sides? Sure, you can do that. Now remember, as soon as you do the square root of both sides, you get plus or minus. In this case, I get plus or minus. I feel like I can kind of simplify the square root of 8, right? Yeah, because the number 8 is the same as 4 times 2, and I can pull out that 4 as a square root of 4, which becomes the number 2, but it leaves behind a root 2. And so I get plus or minus 2 root 2. Now, what's plus or minus 2 root 2? Well, first of all, that's 2 more roots. That's 2 more roots. And if you couple that with the roots that we started with, remember I started with 5 and I started with negative 4, it looks like I got 4 total roots. And isn't that exactly what I was expecting? Yes, it's exactly what I was expecting, 4 roots. And these 2 root 2's that I have right here, well, those 2 root 2's end up being my other 2 roots on the graph. Yes, these 2 points that we saw are valued at 2 root 2 and negative 2 root 2. It's just that I didn't know that until I went through the division and the depression to be able to locate and identify those exact values. And kids, this is how we can use division and depression to be able to continue to navigate our way through some more complicated polynomial problems. So I want you to use those ideas when you do tonight's homework, which will be on that half sheet.